So we're looking at our angle theorems now. And with our angle theorems here, the first one is looking at the idea that we have angles that are subtended by an arc here. So CD is an arc. If we want to draw a chord in there too, these angles can be subtended by a chord as well. So that works the same way. So the idea here is that if we have an angle that's subtended at the center, and we compare that to the angle that's subtended at the circumference here, if you notice what's happening, I'm moving this angle around and it's not changing. So no matter where I go, because it's subtended by that one arc there, the angle's not going to change no matter how far I go in the circle. So you can see it's always going to be 38.9. Now if we look at that as well, compare that to the 77.8. Now if you look at compare those two numbers, hopefully you're looking at that and going, wait on, that angle there is twice the angle there. And that's exactly right. So the idea that if you've got a chord or an arc that's subtending an angle at the center, it's always going to be twice the angle that's subtended at the circumference. So that's at the center, that's at the circumference, and that angle's always at the center is going to be twice the angle that's at the circumference there, standing on the same arc. So notice the lines go here to the center and go to the circumference from the same points on the arc there. Now if I change my arc size, I start to make it larger or smaller, notice again, the angle there changes, but so does that angle there. So 113.02 is twice 56.51. So again, and I can start moving that one, and that doesn't change no matter where you see that occurring. So there we go. That's what we're talking about with the angle standing on the same arc. If we look at another type of situation here, this time when we have an arc here, and we're considering the arc CD, the major arc, rather than the minor arc that we get there. When we do that, we get this type of diagram. So the idea is that if I'm creating this type of diagram, and the arc is there, the CD, major arc CD, I can look at the angle there, 221.36, and compare it to the angle here, which is 110.68 degrees. Again, I can move it no matter where I go. It doesn't change there because it's still standing on that same major arc CD. But again, compare the two angles. The angle at the center is twice the angle at the circumference, no matter where we go. If we change the size of it, then we start to see the angle at the center is twice the angle at the circumference. And it just depends on whether we treat it as a minor arc there at CD and a major arc there at when we move the point D to that point. So CD becomes a major arc there. We're still looking at that angle twice that angle there. We can also get the point where it starts to look there. We've moved our diagram around. This one's probably the hardest one to see, but it's still seeing the angle at the center is twice the angle at the circumference when we start to move it in that regard. We're looking at this arc CD, and that subtends the angle at the circumference. That subtends the angle at the center there. So it depends on where we move that point and where it is to what type of diagram. And we have that diagram, those types of diagram, and this type of diagram here. We can see we start to get that one there. So it's same sort of idea. Now, what is the proof of that? So there's our three diagrams we just saw, those three ideas. So the three situations, and each one we're trying to prove that the angle at the center is twice the angle at the circumference. Sorry, twice the angle of the circumference there. So that's what we want to prove. That one in all those, there's the same labeling in each of them. So what do? We'll construct a line from the center to the circumference there. And then when you look at that and get in all three diagrams, you notice that OC, it would be the same. So OC is going to be the same there as OA because they're going to be equal radii. So OC and OA are going to be equal radii. Angle OCA, so angle OCA and angle OAC, then we're going to be the same as well. But we also know that angle AOM would be equal to angle AOC plus OAC because the exterior angle of a triangle is equal to the opposite sum of the opposite interior angles. So therefore, angle AOM is twice angle ACO or OCA. And you can do the same on the other side. So that angle there is going to be, that angle here, is twice that angle, and this angle here is twice that angle. Well, sum those angles, we get the doubling up effect. So we can start to see whether we're dealing with the angle there, or if we're dealing with a reflex angle in this case. We're dealing with the reflex angle there, or in this situation. So there's our proofs of it. So there's our theorem, and we've got to remember our theorem. Angle subtended at the center, twice the angle subtended at the circumference standing on the same arc. More importantly, we've got to be able to recognize those diagrams in the different forms that they can take. So this one's usually okay, it's pretty standard. But when we start to see these two, that's when it starts to get a little bit tricky to try and be able to pick out that rule. So just be wary of that when you come up to problems. Keep coming back to this theorem and the different diagrams that we do have in there, so you can get familiar with that rule applying to those types of diagrams.